Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to continue our lecture on energetics and thermodynamics. We're going to talk about bond enthalpies. So we've got two things that can happen. Either we're going to break bonds. When we break bonds, that's going to require energy to be put in to break those bonds. And so that's going to be called endothermic. And so see, we have here chlorine gas being diatomic chlorine being broken apart into just single chlorine atoms. Notice that the delta H value is positive, which means that it is endothermic because we are putting in energy to break those bonds. Now here we have a hydrogen atom mixing with another hydrogen atom, and that's going to make diatomic hydrogen gas. And so when we make bonds, it actually releases energy. It's going to be exothermic. And we can see that because the delta H value is negative. Notice that all of these are in the gaseous state. It's very important that bond enthalpies are all written in the gaseous state. That's to reduce the amount of intermolecular forces of attraction, so that the only thing that we are measuring is the actual bond enthalpies. And we're not measuring things like London dispersion, hydrogen bonding, things like that. We're just measuring the intramolecular forces of attractions, or the bonds that we are trying to measure, okay? And that's why we do it in gaseous form. And this is also happening at standard conditions. And so if we wanted to see the change of enthalpy in a reaction, we can take the sum of the bond enthalpies of the bonds broken and subtract it from the sum of the enthalpies of the bonds formed. And we have this nice little table here that gives us the bond enthalpies of various bonds that we might see. One thing to note is that the bond values given here, the bond enthalpy values, are averages of each other. And so the hydrogen-hydrogen bond will not always be 436. However, when they break hydrogen-hydrogen bonds, the average value that they get is about 436 kilojoules per mole. So know that these values are averages, not always constant values. So let's take a look at a problem. Calculate the change in enthalpy using average bond energies. And here we're going to be burning methane. CH4 plus 2O2 will give us carbon dioxide plus water. So the bonds that are broken are going to be in the reactant side. And so CH4 is methane, so there are 4 carbon-hydrogen bonds there, so we're going to break 4 of those. And oxygen molecule is oxygen double bonded to another oxygen. Now there are 2 of those molecules, so we're going to break 2 oxygen-oxygen double bonds. The bonds made, so carbon is double bonded to oxygen in the carbon dioxide molecule, and there are 2 of those bonds. And then in the water, there are going to be 4 hydrogen-oxygen single bonds in there because we have 2 of those water molecules, and each water molecule has 2 hydrogen-oxygen bonds. So again, to figure this out, I need to take the sum of the bonds broken and subtract it from the sum of the bonds formed. Here's our handy little chart. So I'm just going to plug in these values. So the carbon-hydrogen bond we see is 414 kilojoules per mole. The oxygen-oxygen double bond is 498 kilojoules per mole. And if I do that multiplication and I add them up, the total bond enthalpy for the bonds broken is 2,652 kilojoules per mole. Let's do the same with the bonds made. Carbon double bonded to oxygen is 804. Hydrogen single bonded to oxygen is 463. I do the multiplications, and if I add those up, I get 3,460 kilojoules per mole for the bonds made. And then I just look at my formula. I take the bonds broken minus the bonds formed, and I get negative 808. This should be an exothermic reaction. And that makes sense because we are combusting methane, so we're burning something, and it should be releasing energy.